Hello, I am Zhen, and I'll be presenting my FA topic, Sound Event Detection with Human and Emergency Sounds. Sound Event Detection, or SED in short, is the task of recognizing sound events and their respective onset and offset timings in an audio clip. SED is an important field of research that has useful implementations in smart homes and autonomous vehicles. For instance, in autonomous vehicles, an SED system can detect ambulance sirens and prompt the vehicle to adjust its route to give way accordingly. A typical SED system analyzes a waveform in three main steps: feature extraction, frame-wise classification, and prediction post-processing. The purpose of the feature extraction step is to transform a waveform into a feature map that contains condensed information and is suitable for the subsequent stage of frame-wise classification, which predicts the probability of the presence of each sound event for each frame. The last step involves processing the frame-wise predictions, in which the onset and offset timings of the sound events are determined using a set of thresholds. Despite the advancements of SED systems, existing literature on SED have mainly developed systems to analyze audio clips as a whole, and have yet to fully explore the impacts of applying rolling segmentation windows on the audio clips prior to analysis. This is in spite of the fact that doing so may yield potential benefits, especially in real-life applications where audio clips could be hours long and processing them as a whole is not feasible. However, just analyzing non-overlapping audio segments may not yield the best outcomes. For edge cases, such as sound events occurring right at the end of one segment and continue over to the succeeding segment, the SED system may not be able to detect them as effectively as the sound event is broken apart and not analyzed as a whole.
This is overwhelming. To keep your daughter away.
As heard, the speech is broken up and the system may not be able to detect the correct onset timing of the sound event since it begins in the preceding segment. Hence, to remedy this problem, this project focused on developing prediction processing methods that amalgamate the frame-wise predictions of the segments post-analysis. In summary, the primary objective of this project is to develop a well-performing SED system with a limited amount of string-labeled training data, using our novel project dataset as the development set. We also propose prediction processing techniques to address the issues stemmed from processing only non-overlapping segments post-analysis. In our proposed approach, the training system is the foundation of the development of the SED system and is used to experiment with the audio feature types, data augmentation methods, and network architectures. The structure of the proposed training system is as shown on the right. Firstly, we pack the audio into HDFI files to speed up training later on. Secondly, we extract the audio features from the raw waveforms. Thirdly, we apply data augmentation to the extracted spectrograms. Next, we extract the high-level features from them. Then we obtain the presence probabilities of the sound events over the time steps. The prediction system in our proposed approach implements the training system mentioned in the previous slide. It analyzes audio input from the test set and is used to experiment with the threshold types in our proposed prediction processing methods. The structure of the proposed prediction system is as shown on the right. Firstly, we convert the input audio to wave format. Secondly, we apply a rolling segmentation window on the audio. Thirdly, we extract the audio features from the raw waveforms. Next, we use the training system to predict on the extracted spectrograms. Then we amalgamate the frame-wise predictions using our proposed prediction processing methods. Finally, the predictions are compiled and output in XML format. In order to develop a well-performing SED system, we conducted the experiments in the following sequence, which is to first determine the best audio feature type, then data augmentation method, then network architectures, followed by threshold types, and finally the proposed prediction processing methods. Our proposed prediction processing method consists of two main processing steps, which are pre-prediction and post-prediction processing. In the pre-prediction processing step, before the audio is sent to the training system for analysis, we apply a X-second rolling segmentation window with a Y-second stride on the audio input. The values of X and Y are tuned according to a validation stat over the F1 score. However, doing so causes some segments to overlap, and the number of overlaps depends on the position of the segment on the time axis. For instance, if we apply a 5-second rolling window with a 1-second stride on an audio clip, the maximum number of overlaps a segment can have is 4, while the minimum is 0. For the post-prediction processing step, after the segmented audio input is analyzed, we have proposed a method for amalgamating the predictions, which is namely frame-wise averaging. In this method, we first sum the frame-wise predictions together and then average them based on the number of overlaps present in a particular segment. From the table, we can observe that the frame-wise averaging method consistently improves the performance of the SED system. However, it also increases the processing time of the system by an average of 29%. Hence, we need to consider the trade-offs when implementing this method. In order to demonstrate the impact of our proposed averaging frame-wise predictions method on longer audio clips, we evaluated 2 longer audio clips, which we manually labeled using one of our past-performing models. For the baseline, we analyzed the audio clips in non-overlapping 3-second segments. For the averaging frame-wise prediction method, we analyzed the audio clips in 3-second segments with a 0.5 second stride. From the table, we can observe that the system which utilized the averaging frame-wise prediction post-processing method performed better than the baseline system. To better understand the reason behind this, I will now provide a demo of our SED system on longer audio clips. At around the 20-second mark, for instance, we can observe that both the baseline system and the system utilizing our proposed method managed to successfully detect the presence of the explosion sound event. However, the baseline system detected a shorter duration of around 1 second, while the system utilizing our proposed method detected a longer duration of around 3 seconds, which is more similar to that of the ground truth in comparison. In summary, we managed to develop a well-performing SED system using our project dataset and discovered that applying our proposed frame-wise averaging method consistently improved the performance of the SED system and has shown to be especially useful for the longer audio clips. Thank you for your kind attention.